Okay. So we were talking about the convention used in the equation. Okay. And we said when we put plus delta W, we assume that the work is positive when done on the system. On the other hand, in this equation and in this course, we will in general use the second convention. The second convention is the following. So positive here, we do the following convention. That work is a positive when done by the system. Okay, when done by the system. This is why we will put that the variation in energy of my system is equal to the heat minus the work. And for the heat, the convention is always the same. For heat, we consider always that heat is positive when it is provided to the system, so when we are heating the system, and Q is negative when we cool our system. Okay, so for Q, all books use the same convention. However, for weight, some consider that it's positive when done by the system, and they will put minus delta W. And for the one considering that it's positive when done on the systems, I will put plus delta W. Okay. Now, we will define the guys. Can you please mute your microphones? Okay. So we will see that we are 6 main quantities that are useful in describing thermodynamics. We have the temperature T, and of course you are familiar. You cannot hear me? Do you hear me or no?
Yes, clear.
اوكي مش الحال هلا مش الحال كان عندي معلقه.
Okay. So we have 6 main properties to define a thermodynamic state. We have the temperature, the pressure that you already are familiar with. We have the specific volume. The specific volume is defined as what? It's the inverse of the density. Okay. So the specific volume is 1 over rho, and its unit is meter cube per kilogram. And whenever they say for you specific, when they say specific, this means that it is per unit mass. Okay, so we have the specific volume in meter cube per, sorry, here it's kilogram. Okay, per kilogram. And the specific internal energy, the internal energy, we introduced it in the previous slide. And in the following slides, we will learn what is the specific enthalpy and what is the specific entropy. Okay, so until now we know the first 4 properties, T, P, V, and U. We will introduce in the coming slides 2 remaining properties, which are the specific enthalpy and the entropy. Now, for the internal energy, the definition is as follows. Internal energy is an extensive property because it depends on the mass of the system. So when we just talk about internal energy without saying specific, it's extensive. When we say extensive property, this means that it will depend on the mass. And in general, in tables, we will see together today that thermodynamic properties are in general tabulated in tables. So for each fluid, you have a table telling you if I have this temperature and this pressure, I will get the following internal energy, enthalpy, entropy, etc. Okay. Now, the extensive properties, and we put their symbol as like this here. So it's capital letter U. It's depending on M. But to have a general table, in tables, we will not put big U, we'll put small u, which is the specific property, okay? The intensive property, we say. So it's M, the mass times U. So in general, all our all our values will be reported per unit mass to be general, because you know that a table can be used in any problem. So I will use it per unit mass, and depending on my problem, I will multiply by the mass to get big U. So the intensive properties are given in small letters. Okay, so you have the symbol U will give you the internal energy per unit mass, as we do for the specific volume. Okay, so for the volume we put the symbol as big V, and for the specific volume it is small v, so m times small v. Now, we will see together that when we do analysis of a system, we will a new property will appear, which is called enthalpy, and we will learn together here what is the definition of enthalpy. So in analyzing specific types of processes, we frequently encounter certain combination of thermodynamic properties, which are therefore also properties of the substance undergoing the change of state. And we will illustrate this by defining enthalpy. And enthalpy is defined from the quasi-equilibrium constant pressure process. But we will see after that this property is very used and is very useful for us. This is why we added in the tables to U and specific volume and other properties. Okay, let us see this small example to understand how sometimes when doing analysis we come up with new properties that might be helpful. So if you consider the constant pressure quasi-equilibrium process, if we have here a certain gas, okay, and it's undergoing a change in volume due to heat. Okay, we are heating the gas and it will expand. Okay, and this process is taking place at constant pressure. If we want to do the analysis of this case, we will write the conservation of energy. Okay, we will write the first law of thermodynamics. The first law of thermodynamics will state that the heat provided to our system, because if you go back to the equation, okay, what was the main equation? That any variation in energy, so if you go to the previous slide, any variation in energy dE is due to variation in internal energy plus variation in kinetic plus variation in potential. Now, here, since you have air in a tank, the change of air altitude is not very important, and you know that the density of air is very small. This is why for air we can neglect, so we can neglect variation in potential energy. Plus also here that we can assume that here, because it will expand, and the variation in kinetic energy of particles will be small compared to the variation of internal energy. This is why when in problems, when they don't give you data about the kinetic energy, you can consider that its variation is negligible compared to the internal energy, especially that you are working with a gas. Okay, so here in this problem, if we apply this relation, what do we get? We get that the variation in energy of my system is due to the heat we are putting on my system minus the work done by my system. But if I go back to the problem, they said that this process is at constant pressure. And I want to tell you that in general, the work on a system or by a system, okay, we define it by what? Any idea? How we define the work done on a system or by a system? Okay.
رو دي بي دي في
Yes.
أو في دي في حسب.
Yes. Okay. The work done on a system is equal to, between state 1 and state 2, is integral from 1 to 2 of PdV. Okay, and here I want to tell you, your friend said that it's or PDV or VDP. I want you to pay attention. Here you have a closed system. When you have a closed system, you don't have a flow inside. So we will see after, when we develop the thermodynamic law for a certain system, we will see that we have two types of work. We have work that is performed on a controlled volume, and we have work due to flow, to a flow. Okay? Do you have a flow here? No, it's a closed system. When you have a closed system, then you will only consider the work done or performed by the system. There is no work of a flow. So the work formula in this case will be integral PDV between state 1 and state 2. But since they gave us the assumption that pressure is constant, because in the given they told us assume constant pressure, the pressure term will get out of the integration, and we will get that the work here, can you tell me the work will be done by the system, or we are putting it on the system? Which case is here?
أي volume أكبر يعني is the system expanding or is it being compressed؟
Yes, it is expanding here. Why it's
إذا كان done
expanding?
by the system.
Yes, very good. Because here, look, what is happening here, you are heating the gas. When you heat the gas, you will increase its energy, and this Q will be divided into two parts. An increase of internal energy plus a work done by the system. Okay? So here, your gas will expand because its temperature will increase. And as it expands, the volume will increase. And therefore, my system is doing a work. How can I understand that it's doing a work? It's displacing the piston upward. So it's able to, you know, that work in general, the formula you are familiar with before for the work, if you remember, work is force times distance. Okay, F times D. Okay, but here the force term can be written as pressure times area. Okay, so this is why we can say that we can define work done as P delta V, because the work is F delta of a distance, delta X. Okay, and the force can be written as P times A. So now you have P times A times delta X. And you know that area times displacement will give you what? Will give you change in volume. This is why we say here that the work is performed on this system is equal to, this is elementary work. Okay, if I say dW or delta W, okay, delta W equal to PA delta X. So we have that it's equal to P times dV. This is why we say that the work done by the system is given by P integral PdV. So if I want to find the total work, I should integrate my expression, and I will get that the work is integral PdV. Okay, and this is the expression of a work done by the system. It will be positive if my system is producing work, and here it is the case here, because look, the volume is expanding. V2 is larger than V1, so my system is producing work, and I will get a positive result when I do integral PDV. So now, if I come back to my, yes?
بس في نديم عم بجرب يفوت على الصف. He's in the waiting room.
Yes, sure. Okay. So now I can say that the work term can be replaced by P times V2 minus V1. Okay. And now if I replace into my equation, okay, if I go back to my thermodynamic law, first law, what was my law? That Q, delta Q, okay, so the heat provided to my system between state 1 and 2 minus W between 1 and 2 equals to what? The variation of my energy. So it's energy at state 2 minus energy at state 1. But we agreed together that in this case, because it's air, it's a fluid, the variation in potential and kinetic energy are very small compared to the change in internal energy. So I can replace this term by internal energy at state 2 minus internal energy at state 1. Okay, and now the equation will be as following. I have that sorry, I have a little problem here. Okay, I have now that the energy I provide to the system, Q2, is equal to U2 minus U1 plus my work. And my work is P delta V. So it's P2 V2 minus P1 V1. And we said that the pressure is constant. So P1 is equal to P2. Okay. And now what we observed here is that we can take state 2, the terms of state 2 together. We have a new term, U plus PV, okay? Because we found that the variation, the heat is equal to the variation of this property for my system, because it's U2 plus P2 V2 minus U1 plus P1 V1. From here, we said it will be of interest to define a new property for a system, which is called the enthalpy, and it's defined as the internal energy plus PV. Now you will tell me, but it's just a particular case here, and why we define a new property? We will see together that when we have a flow, so it's not a closed system, when we have an open system where you have flow of a fluid entering and leaving, the enthalpy will appear again, and it is of high importance. This is why we will add this new property to the other thermodynamic properties, and H is computed as U plus PV. Any question on this? Okay, so let us continue. Now, until now, we have introduced the first law of thermodynamics for a certain control mass. And look, when they say control mass, they mean that we are taking a fixed amount of mass and doing the analysis on it. So we are working on a closed system. Okay. Now we will expand our analysis after two open systems. When we say open systems, as I mentioned before, you have then a certain control volume, and you have a flow that is entering your system and another one that is exiting your system. Now, this equation can be derived with respect to time. So I can put it as a rate equation. All I have to do is to derive with respect to time. So I can say that the variation of energy of a control mass with respect to time is due to the heat rate minus the work rate. Okay, so all I did that is now I'm expressing my equation per unit time. And we will see after that whenever I have a flow, inlets and outlets, we will work on the energy per unit time. Okay, because we have a certain mass flow rate and everything will be defined per unit time. Then we will apply the following relation. And in this relation, what is the unit of all my terms?
What?
Watt. Because the energy unit is joule, and here I am defining energy per unit time. So it's joule per second, okay, or what we call it's watt. Okay. Here, for example, we represent a certain scheme illustrating the different terms in the energy equation. So let us consider this system, for example. What you have here, you have a certain turbine, okay? And this turbine is driving a shaft. So in general, for example, we will see if I take a steam turbine, what is the idea of the turbine? It will try to take the energy from steam to convert it into another form of energy. So here you have this is an open system here because you have flow of energy. Okay. So first you have here an inlet, okay? You have an outlet, and in this system, what is happening is that steam flowing inside your turbine is losing from its internal energy, and this will convert energy into another form, which will turn the shaft of the turbine. Okay. On the other hand, when your steam will exit the turbine, you will heat it again because when entering the turbine, it will lose its energy, part of its energy to rotate the shaft. So at the exit, for example, you can provide heat to increase the internal energy again of my steam. And when heated, this steam can produce a work, for example, as we did in the previous example. Since once heated, it will expand and it can, for example, push a piston up. So it will produce a work. And then it can, when we finish this, the steam will exit. So this is an example how in this system we are exchanging energy in several forms. Okay. Now, until now we have considered the equation for a closed system. After we will write together the equation for an open system where we have flows entering and leaving our system. Okay. So now, so as we said, sometimes we have an open system, it's not closed. So we should consider another type of work, which is the work of the flow. Okay. So if you have a fluid flowing across a control surface that is entering or leaving with a certain amount of energy per unit mass, we should take into consideration the energy of this flow, because first, this flow can increase the energy of our system, because imagine that I have a flow entering a system at a very high temperature. As it goes through my system, it will lose of its internal energy and it will exit at a lower energy. So the mass flow rate that is entering and leaving will affect the energy of my system. Plus, not only for heat, but also for work, because when flow is entering, as you can think about it, it's pushing, let's say, fluid in my system. So it will produce a certain work that we call the workflow. Okay. And the workflow is calculated as following. So first, we should consider, for the fluid entering or leaving, we should consider its energy, which is computed as following. So the energy of a fluid that is entering or leaving is equal to the summation of its internal energy, kinetic energy, and potential energy. Okay. And as it is flowing through my system, I should know what is the energy at the inlet and what is the energy at the outlet, to know if my flow will add energy or will take energy from my system. Okay. So if it will enter at a very high temperature and it will exit at a small temperature, this means that if I'm talking about for same velocity and potential, okay, then the internal energy will be much lower. This means that this fluid gave energy to my system. Okay. On the other hand, also I should look at the work it's performing when it's entering and leaving my system. This is why we define what is called the flow work, the rate of flow work. And as I told you before, we have, when we take a control volume, we should consider two types of work. We should consider the work that is given to the control volume or lost by the control volume. Plus, we should consider the work through boundaries that are entering or leaving my system. And the workflow is defined as following. Okay, the workflow is what is d work by dt. Okay, d work by dt, and we already defined the work as force times distance. Okay, so it's equal to derivative of force times distance by time. So considering that here for a certain force, okay, for a certain force of my, if I consider at one section that the force is constant, I can get it out, and I will get that it is equal to F times, so it's equal to F times derivative of distance with respect to time. What is the derivative of move distance with respect to time? It's velocity. Okay, so derivative, I will call it x to not have confusion. So fx, okay, so I have f times dx by dt, which is equal to f times v, where v is the velocity of my flow. Okay, so replacing F by PdA, because you know that force is pressure times area. So elementary force will be P times dA, and integrating, considering that for a certain sections I have the same pressure, I can write that the workflow is equal to PV dot. What I mean by V dot here? What is V dot? You know, if I do yes, if I do velocity,
Volumetric theory.
yes, when I do velocity times area, the unit of velocity is meter per second, okay, and the unit of area is meter square. So I get the volumetric flow rate. Okay, this is Q. Sometimes we name it Q, or if you want here to not confuse terms, they name it V dot. Okay, V dot, which is volumetric flow rate, and the unit of it is meter cube per second. Okay, so it is in meter cube per second. And you know that the volumetric flow rate can be related to the mass flow rate by which relation? It's equal to the mass flow rate m dot over what? Over the density rho. Okay, because m dot is the mass flow rate in which unit? In kilogram per second. Okay, and rho is in kilogram per meter cube. But now we define together what the property of specific volume. What was the specific volume?
1 over rho.
1 over rho. So we can replace 1 over rho by the specific volume, and then we can replace V dot by m dot times V. V, and V is here the specific volume. Specific volume. Okay, so I know that you have several V in this equation. I don't want you to confuse between them, so I will just repeat here. The first V is velocity, okay, and so V here is velocity, and here V dot is volumetric flow rate, okay, and the volumetric flow rate is the specific volume times the mass flow rate m dot. So we will see that the workflow that is entering or leaving can be computed as P times specific volume times m. Okay, any question until here? Okay, so let us continue now. Okay, now this is why what we will do now, we will consider that we will define a certain term called the energy plus PV, because as you can see, the term PV is important due to the workflow. So if we compute E plus PV, what do we get? We get the internal energy plus PV plus half V squared plus GZ. And U plus PV is what? The internal energy plus PV represents the enthalpy. This is why I told you that we will use this term again. Okay, because in an open system, we will see that the internal energy term will be added to PV term, and we can replace this summation U plus PV by H. So we can say that now we will use H plus half V squared plus GZ, and let us see why. Because as we have seen together, okay, if I have an open system, so here I have a system, and I have a flow that is entering and leaving this system. What will change in my thermodynamic law? So first, my thermodynamic law states that the variation in energy of my control volume is equal to the heat provided, okay, minus the work done by the control volume. But also here, okay, I have another type of heat and another type of work done, because the flow that is going inside and outside is producing a work and or it's giving heat or taking heat. So how do I account for this? In addition to any heat that can be done on the system, so here when they just say Q dot control volume, they mean, for example, Q from an external source. So if you have fire, for example, here, if I have fire here, it will give heat to my system, and it is from an external source, okay? And if I'm doing, let's say, if I have a piston and I'm pressing on it, also I am giving a work from an external force or external side. But I should add to this possibility, which comes from external environment to my control volume. I should add the effect of the flow, because also the flow when entering, it will give me a sort of heat, okay? It will give me the heat due to its internal energy. So I should add, if you want, this term is due to the heat provided by the flow. So I should do plus m dot inlet times energy of inlet and minus m dot outlet energy outlet. So these two terms are mainly due to, so this is heat provided by the flow. This is heat provided by the flow, okay? While this one, Q dot control volume, is the heat provided from outside of the control volume, okay? So while here this term is heat provided by external sources, by external sources, okay? And also for the same for the work, okay? For the work, we should take into consideration any work done by external sources, but also we should take into consideration the workflow. And we just defined together that for a flow, what is the definition of workflow? W dot is equal to m dot, okay, times specific volume times pressure, okay? So now for an inlet, the inlet flow will do a work on my system, okay? This is why here, when I consider my case, I will put this work due to the flow energy will be plus m dot I E plus m dot I pi vi, and for the exit flow, it's minus m dot exit PEVE. So now, if you want, I can take in common m dot into factor m dot inlet. I will have the term, a new term that I defined before, okay? I have this term, which is the energy plus PV. And if I replace the energy by its value, which is U plus half V squared plus GZ, I will have the term that I defined previously, which is the enthalpy. This is why I told you when you have an open system, you will work with a new property, thermodynamic property, which is the enthalpy. Therefore, here, when I do the replacement, I can say that the change in energy of my control volume is equal to heat that is provided by external sources minus work done by done on my system, okay, and plus the flow energy, which is calculated by plus minus plus mass flow rate at the inlet times the internal enthalpy plus the kinetic and potential energy, and minus m dot e at the exit times the enthalpy and kinetic and potential energy. Now, in general, if they don't give you information, you neglect velocity. In general, velocity and potential will be negligible unless they give you data about them. So if they give you the inlet and exit velocity and they give you the elevations, so it will be good to include them. But you will see in problems that we will do that even if I include them, their effect will be very small, because in such systems in general that we will deal with, steam power plants, the dominant effect is for the enthalpy. Okay? So now, what we can understand from this equation is that the rate of work is the sum of all shaft work terms and boundary work terms, because we will not only consider the work from external sources and the heat from external sources, but also the work and heat due to our flow. Okay? Now, so this is the general rule. If you have several inlets and several outlets, you can put your equation into the following form. So the only modification you will do is that you will do summation of mi times hi plus half vi squared plus gzi. So if you have several inlets, we should do the summation of energy that is getting in. And if you have several outlets also, you should do the summation. In general, if we have one inlet, one outlet, so no need to do any summation. Okay? Now, we can, in general, to simplify this equation, we can replace this term, which is hi plus half vi squared plus gzi. We can replace it by h total. And as I told you, in general, these two terms can be neglected compared to h. So my final relation will be of the following general form, and we will see how to apply it on different systems together. Okay, so I will open a new session to continue.